coding the neural network in Keras is quite simple. What we will do is we will put model equals sequential when shell, and here we just declare that we will add different layers to this model, and then we start adding these layers. So model equals, or model dot add. The first layer will be convolutional conv 2D, and it's going to be 64, and the stride, which is or the kernel size, it will be 3. The padding is going to be the same, so the size of this network is not going to change. Activation equals ReLU, and I need to put another activation is ReLU of this convolutional network. Now the shape of it is going to be input shape is going to be x dot shape and 1, which is 120, 120, and 1. We don't have this because this is just the number of images. This is what we're interested in. And of course, you can just write it 120, 120, and 1. But this way you can change the size and it will change the automatically. So model also dot add max pooling. This is the pooling layer 2D as well. And here I think, yeah, the syntax is here. And once you have done this, you have another layer of convolution 2D layer. Of course, all of what we do is convolution 2D, and padding also no change in size. The activation also ReLU, and we add another layer of max pooling. Now after that, this architecture will be 128. It just will have 128 filters, and we will also do max pooling. After that, we will flatten our network dot add flatten our network. And now we will, of course, once we have this, we can of course add dense layer, fully connected layers. In this case 256 with activation also ReLU. We add also the dropout to make our network more robust, avoid overfitting. And also model dot add patch normalization. We added this area, patch normalization, and after we do that, we will add the decide, like with the final decision kind of dense to activation. Of course, here we can choose anything we want. We can choose softmax, or we can choose Sigmund function. it's 2, so we can say it's sigmoid. But you can try other like softmax. I think it will work. Model dot summary, and we shift enter. We have a problem. To reloop place. Activation. Sorry, we have here. We just move this one. Sigmoid. Yeah. So this is we decide our. I think we should put like this. Yeah. So here is our network, and here is the number of parameters that we need to solve. You can see that even for this small network, the total number of parameters is 7.5 million parameters. So it's quite a big number. And here is just simply it will show you the size of the every layer in here. The flatten at the end, it will end up with about 29,000 uh, neurals, the size of it. So now what we will do is we will teach our algorithm. We will fit our model. So optimizer equals Adam, and learning rate. Also, this is, you have to try different values. E minus 5 model dot compile, and we put a loss function, and this design is sparse categorical cross entropy, and we decide the optimizer. So as you can see, it's these libraries makes things much easier. The metrics is we will fit on accuracy, history, and this is going to save some parameters of our model. Dot fit, we need to fit x to y, and we need to have epochs of, we can say 18 epochs, so it will train 18 times. And the patch size equals 128. These are going, the model will take, so we will have 20,000 data points, and this 20,000 data points will have a patch size of 128. They will be cut, and these going to be fed to the network, and then it will train on these 128 patches, and then another patches will come, and when we update the weights again and again. Validation split equals 0.25, so a quarter of the data is going to be used for validation. And I'm not sure about this exact solver, but in many times in neural networks and in machine learning, we take this 25%, and every epoch we change this 25%. So the data going to be trained on all the training data. In this case, we didn't split the data to training and testing data, but in the next lecture or the next example, we will do that. For now, we just need to build the model and train it as a beginning. So with that, we are already finished, and the next step is going to be just run the model, and as we always do, shift and enter. Here we have accuracy optimization. So I forget just to put here the equal sign, and we run it, and now it starts to train. So now it's finished the training, and what we will do now, of course it has a very high accuracy level. Here we can see the accuracy level is quite high. On the validation part, and the validation loss is low. Accuracy level also in the training part is high. So what we want to do is, because we put the data into history, we want to see some of the data. Of course, history is actually keeping some information or a lot of information in for this training process that we can plot. So we can see that in keys, which has loss, accuracy, validation loss, and validation accuracy. So what I will do is, here I want to copy paste part of the syntax in which we will print or plot this accuracy level. This is just a syntax to just a plotting, doesn't have really machine learning value. So you can see here that the training start, of course, even from the first epoch of 90%, which is quite high, and then it will shoot up until kind of like saturated, but keep going after even epoch number 18. Keep in mind that, of course, the validation also increases. The validation part also increases. Now, in loss, on the other hand, it will start the opposite, high, and then it will keep decreasing, and the validation set will also keep decreasing. In the next example, we will having a different sets of training set and testing set, and after that we will test it on the testing set. However, in this case, we only train on our training set, and the validation is part of the training set, which is like not 100% correct, but the process is the same. for our training. Now, after finishing the training, what we will do is we have to save our model, because as we see, training takes a lot of time and and a lot of processing power. So most likely you cannot use this computer, or if you're training on the cloud, like Google Cloud or Amazon Cloud, you will have to pay money. So what we will do is, after it finishes training, we save the model, and in this case we save it in the same location, and I'll just call it trained model 1. So after that, this is going to save the model, and we shift enter, and we can see already in our file that we have a new file, which is you can see here is called trained model, this file, and this is its size, and so not so big size. So in order to get this to reload this trained model, we say another like model number 2 or test model, whatever model you want to put the values in it, and keras dot models dot load model, and again you just take the model location and shift enter, and this is we already upload the model.